Now we'll consider the speed of the wave. So the speed of a mechanical wave, and I've put the word mechanical in here to differentiate it from a light wave, is determined by the properties of the medium through which it travels. The equation is the velocity of the wave equals the square root of the elastic property divided by the inertial property. So for waves like sound waves, which are compression longitudinal waves travelling through a fluid, the velocity equals the bulk modulus of that fluid divided by the density of the fluid, where B here equals the bulk modulus, and this is a measure of the compressibility of the fluid. It's measured in units of pressure, pascals, and rho here is density, which is measured in kilograms per meters cubed, remembering that density equals mass per unit volume. This means that the wave speed is all about the medium. So what the equation we wrote down on the previous slide says is that if we have a higher bulk modulus, we have more restoring force the faster the wave moves, and if we have a higher density, we'll have more inertia and the slower the wave moves. We'll write out the equation again. V equals the square root of B on rho. Let's have a look what's not in this equation. There's no term for amplitude here, and this is somewhat counterintuitive, so it's worth spending a moment thinking about this. Try and make a transverse wave with a heavy rope. So you take the rope and you give it a flick down one end, and the wave propagates down to the other end. The question is, how can you increase the velocity of that wave? You might think that if you shake it harder, i.e. you change the starting amplitude, you give it a higher starting amplitude, you would be able to make that wave propagate faster through the medium of the rope. However, this is not the case. Shaking the rope does not result in a faster wave.